Hi everyone, welcome back to Civil Engineering with Amir. This is Amir here with another question from Craig's Mechanics of Materials or Solid Mechanics on the topic of axial deformation of members with varying cross sections. Before we get into solving this question together, if you're new here and haven't subscribed to the channel yet, don't forget to hit the subscribe button on the right corner. That's the best way you can support us and help the channel's growth. Alright, now let's read the question together. In this question, you can see a conical frustum with a length of L and modulus of elasticity of E, which is homogeneous. The diameter of this rod changes from D0 at the beginning and 2D0 at the end linearly, and it's mentioned that D0 is very smaller than the length of the rod. You can also see an axial load P is applied to the ends of this rod. And now the question wants us to determine an expression for the stress distribution on an arbitrary cross-section at a distance x from the beginning. And we also have to determine an expression for the elongation of the rod. Okay, let's start solving the question. In part A of the question, we have to determine an expression for sigma x at a distance x from the beginning. So we can first cut the rod from this distance x, and we will have something like this. So we have a force P applied to the end. This is x from the beginning, and we will have a force called nx. And we want to find an expression for this nx at an arbitrary distance x from the beginning. So we can write the equation of equilibrium in the x direction. We have sigma fx is equal to 0 in this direction. We have nx minus p is equal to 0. So our nx will be equal to p and is constant. So no matter at what distance we are from the beginning, this is independent from our x, and the axial load is always equal to P for this rod. And now in order to determine an expression for the stress at this arbitrary cross section, we have to determine the area of this cross section at distance x from the beginning. So this area. So if we draw the whole bar, this is a little bit exaggerated, but that's okay. This is going to be our cross section at distance x. So this is x. This whole length is L. This is D0. This is dx. And this is 2d0. Now, if we consider this triangle, this length here will be equal to dx minus this d0 divided by 2. So this total length is dx, this is d0, and we have 2 halves of dx minus d0 divided by 2. And now if we call this triangle ABC, and this is D, this is E, using the geometry relations, we can say DE divided by BC is equal to AD. So DE BC is equal to AD divided by this total length, which is AB. So DE is this value, which is dx minus d0 divided by 2. BC is this 2d0, minus d0 divided by 2. So this is 2d0 minus d0 divided by 2. AD is equal to x, and AB is equal to L. And now if we simplify this, we can write dx minus d0 divided by d0 is equal to x divided by L. So our dx will be equal to d0 divided by L multiplied by x plus d0, or dx will be equal to d0 x divided by L plus 1. Now, since the cross-section of this rod is circular, so the area of the circle at this section will be pi divided by 4 multiplied by the diameter of the circle in the power of 2. So we can say AX will be equal to pi divided by 4 dx in a power of 2. And we can use this dx in this equation, so we can write AX is equal to pi divided by 4 d0 in the power of 2 x divided by L plus 1 in the power of 2. Now that we have the resultant force at an arbitrary distance x from the beginning, and we also have the area at that same distance, we can write an expression for the stress at this distance. So we know this resultant force has an expression like this: nx is equal to the integral of a sigma dA. And we also know that whenever the normal stress is constant over a cross-section, so at each cross-section, the normal stress doesn't change. So in this cross-section, at each point, the normal stress is going to be constant. So in this integral, since this sigma is going to be constant at each cross-section, we can bring it outside of the integral and simplify it. So sigma x, the integral of a, and this will be our ax. So we can substitute nx with its value, which is p, and then simplify the whole integral as sigma x ax is equal to p. So p is equal to sigma x ax, and sigma x will be equal to p divided by ax. And for ax, we can use this equation. So sigma x will have an expression like p divided by pi divided by 4 d0 in the power of 2 x over L plus 1 in the power of 2, or sigma x will be equal to 4p divided by pi d0 in the power of 2 x over L plus 1 in the power of 2. So this will be the answer for part A of the question. And in part B of the question, we have to determine an expression for the elongation of the rod. We know the elongation of the rod can be determined by taking an integral of the force at each cross section multiplied by dx divided by a e. We have the value for nx, we have the equation for ax, we have e, so we can simplify this integral by 0 to L P dx divided by pi divided by 4 d0 in the power of 2 x over L plus 1 in the power of 2 multiplied by e. And we can bring these constant values from the integral to the outside. So this will be equal to 4p divided by pi e d0 in the power of 2 integral of 0 to L dx divided by x L plus 1 in the power of 2. And if we calculate this integral, we will have an equation like negative L divided by x over L plus 1 from 0 to L. And this will be equal to negative L divided by 2 minus negative L divided by 1 or L divided by 2. So this whole equation will be equal to 4p pi e d0 in the power of 2 multiplied by L divided by 2, and e will be equal to 2pl divided by pi e d0 in the power of 2. That's it. So in part A of the question, we first determined an expression for the resultant force at an arbitrary distance x from the beginning of the bar. We then determined an expression for the diameter of the cross section at that same distance, which can be seen here. And then we wrote an expression for the area of that cross section. And based on the force and the area, we wrote an expression for the axial stress at an arbitrary cross section. So that was part A of the question. And for the elongation, we used this expression. We had the value of n, we had the expression for our area. And by putting these values in the integral, we determined the total elongation of the bar, which is 2pl divided by pi e d0 in the power of 2. Thanks for watching this video. If you liked it and found it helpful, please give it a thumbs up. If you have any comments, suggestions, feedback, or even if you have any questions, please feel free to write for us in the comment section. And finally, if you haven't subscribed to the channel yet, please hit the subscribe button on the right corner and support us. Thanks again for joining me today, and see you in the next videos.